Welcome to this explainer. Today, we're jumping straight into a massive cosmic detective story, and we're heading all the way out to the edge of our solar system to investigate two of our most mysterious neighbors, the ice giants, Neptune and Uranus. We're going to unravel a really bizarre puzzle about their off-kilter magnetic behaviors. And by the end of this, you're going to see exactly how a completely wild, almost magical phase of matter, super-ionic water, shapes the planetary magnetic fields that shield these worlds. Okay, let's dive right in.
So I want you to imagine holding a regular compass. Here on Earth, it reliably points to magnetic north, which is, pretty close to our actual geographic North Pole. But what if you were floating above Neptune? Well, your compass would be totally, hopelessly confused. Neptune's main magnetic axis is tipped over by an absolutely staggering 47 degrees compared to the planet's actual rotation axis. And Uranus? Uranus is even more extreme, tilted by about 60 degrees. I mean, how does a massive planetary magnetic field end up tilted practically halfway to the equator?
You see, we're really used to Earth's orderly, aligned dipole magnetic field. It's neat, it's compass-friendly, and it originates from a molten iron core that perfectly aligns with our planetary spin. But Neptune, because of that severe tilt, Neptune's magnetosphere undergoes these wild, chaotic variations with every single rotation. And it's not just messy, it's incredibly intense. This shifting non-dipolar field is about 27 times more powerful than our magnetic field here on Earth. 27 times. To figure out why, we have to look deep inside the planet. Section 1. Descent into extreme pressure. To actually find the culprit behind this magnetic weirdness, we have to sink down through the planet's outermost layers. Now, the first thing to remember is that Neptune doesn't have a solid surface. You absolutely cannot land a spacecraft on it. Instead, you'd be descending through a really deep atmosphere made up mostly of hydrogen and helium, plus a little bit of methane. And that trace amount of methane is crucial. It absorbs red light but reflects blue, which is exactly what gives Neptune that beautiful, vivid blue color. As we go deeper, this thick gas doesn't just hit a rocky crust. It gradually thickens and merges into a dense slush of water and melted ices. Now, as we transition out of that gaseous atmosphere and into the icy depths, the conditions become, almost incomprehensible. Deep inside Neptune, the pressure is crushing down at over 1.4 million times Earth's atmospheric pressure. 1.4 million. Just imagine the entire weight of Earth's atmosphere and then multiply it by over a million, pressing against every single square inch. And under that mind-bending pressure, things get so unbelievably weird. NASA data actually points to this crazy paradox. Scientists think there might be an ocean of super hot water hiding under Neptune's freezing clouds. And get this, it doesn't boil away because the incredibly high pressure literally keeps it locked inside. It's an ocean thousands of degrees hot, but it is physically incapable of boiling because the immense weight of the entire planet above forces it to stay in a condensed state. Section 2. The super ionic state. So here is the really crucial takeaway. Water under these conditions does not behave anything like the water coming out of your kitchen tap or even the ice sitting in your freezer. Based on advanced simulations mapping temperature and pressure, we know that as you descend into Neptune and hit temperatures exceeding 3,000 Kelvin at those immense megabar pressures, molecular water completely bypasses standard ionic stages. It transitions directly into an entirely new state of matter. We call this the super-ionic phase. But, what exactly does super-ionic even mean? Let's define this because it's pretty alien. Super-ionic water is essentially a hybrid phase of matter, a two-component system. Under these extreme conditions, water molecules actually break apart. The oxygen atoms lock into a rigid crystalline solid lattice, but the hydrogen atoms, the protons, they don't lock down at all. They detach entirely and just diffuse freely through that oxygen lattice like a liquid. So it's technically a solid and a fluid at the exact same time. Honestly, it's mind-blowing. And here is the truly surprising part. You'd probably assume that a solid lattice of oxygen would make this whole layer incredibly stiff and rigid, right? Actually, no. Despite having a solid oxygen structure, super-ionic water responds to stress almost entirely like a fluid. Because of all those freely moving protons, this bizarre phase can seamlessly flow, swirl, and convect beneath the crushing weight of the planet, just like a thick, dense liquid. Section 3. The planetary dynamo.
Okay, so how does this actually solve our big mystery? We need to connect the dots on how this flowing hybrid water creates those massive tilted magnetic fields we talked about at the start of this explainer. When we look at interior structure models, we find that this super ionic water doesn't just form a little puddle. In Neptune, it forms a massive planetary scale shell that starts at about 62% of the planet's radius and wraps entirely around the rocky core. It's a colossal shell of exotic matter. Let's walk through the exact aha moment step by step. Number one, as we established, this superionic water shell behaves dynamically like a fluid, so it's fully capable of motion. Number two, because it is absolutely packed with freely moving protons, it has massive electrical conductivity. And when you have a massive electrically conductive fluid churning and rotating with a planet, boom, you get a dynamo. Finally, number three, because this dynamo is generated way out in this outer fluid-like shell, instead of a deep central point like Earth's core, it generates a completely off-center, highly tilted, non-dipolar magnetic field. For a planetary dynamo to actually work, though, the math has to be absolutely perfect. And it is. The specific electrical conductivity of this flowing proton fluid inside Neptune is incredibly high. In fact, this massive conductivity perfectly matches the physical requirements that scientists have calculated in advanced 3D simulations to sustain what they call a thin shell dynamo. The numbers perfectly align with what the Voyager 2 spacecraft observed all those years ago. So let's tie this whole cosmic detective story together. We finally solve the magnetic mystery, the ice giants, by understanding this very specific planetary geometry. Basically, there's a small, or maybe even absent, rocky core, which is surrounded by an unmoving, stably stratified inner layer of superionic water. And sitting right above that is a thinner, highly conductive, fluid shell of ionic water, taking up about a third of the planetary radius. The churning of that electrically charged outer shell perfectly explains the wild 47-degree magnetic tilt Voyager 2 sent back to Earth. Mystery solved. Section 4. The Final Frontier. Now that we've figured out what happens deep inside Neptune, let's take a quick look at the mystery still waiting to be unraveled right in its backyard. Take its largest moon, Triton. Triton is actually a captured Kuiper Belt object, and it has a surface age of less than 100 million years, which is incredibly young in geological terms. It's got active plumes and this unique cryovolcanism where freezing ices erupt just like lava. Scientists now think that the initial heat from when Neptune captured it, combined with ongoing tidal forces, means Triton might be hiding a massive subsurface ocean right now. It's a completely different kind of water mystery orbiting the exact same planet. And that brings us to a final, really provocative thought to leave you with. We know that Neptune-like planets, ice giants, are actually incredibly common throughout the wider galaxy. We've already discovered tons of exoplanets with similar masses and radii. So, if this exotic superionic water is what powers the magnetic shields of our local ice giants, completely defying the Earth-like iron core model, what does that mean for the rest of the universe? What kind of alien oceans and bizarre superionic magnetic shields exist on exoplanets far, far beyond our solar system? Could these totally unique magnetic fields be shielding entirely new types of habitable worlds? It completely changes what we're looking for. Thanks so much for joining me on this explainer, and I hope this deep dive into the ice giants keeps you looking up and staying curious about our cosmos.